Glider A moves in the horizontal slot with a constant velocity v for a short interval of motion. Determine the angular velocity of the bar AB in terms of xa, v, and L. So for this question, because it's quite simple, we're going to be able to just create a geometric relationship between some different properties in order to get this answer out. So what we're looking for is the angular velocity of the bar. So let's say that I'm going to measure the angle in here, theta, and I'll call that the direction of the arrow, the positive direction, I guess, or the way I'm going to measure theta. So what that means is if I call this the angular velocity of the bar, omega AB, what I know is that the rate that this angle changes with respect to time is going to be equal to the angular velocity of the bar. It's as simple as that. So we can say that omega AB is equal to theta dot, the rate this changes with respect to time. So now all we need to do is create a geometric relationship using triangles, and then when we take the derivative of that geometric relationship, we should end up with theta dot in the equation, and obviously then we just need to solve for it. So let's take out the triangle. So this we're calling theta. We know the angle that sits in here is always going to be 60 degrees because the slots are fixed. And we'll call this length XA, and this is L, the length of the bar. So we can see that this triangle is not a right angle triangle, so we're not able to use sine, cos, or tan. What we're going to be having to use instead is either the sine rule or the cos rule. So just as a reminder, the sine rule is A on sine A equals B on sine B. And the cos rule is this one here. Oops, sorry, it's minus. Okay, so the main difference between the two different rules is the number of angles and sides that you need to have to be able to use the equations. So for the sine rule, you need to have two sides that you're wanting to relate together and two angles that you're wanting to relate together. However, for the cos rule, you need to have three sides and one angle that you're trying to relate. So if we look at our diagram that we've drawn here, we can see that we've really got two angles that we want to work with, and we've also got two side lengths that we want to work with. So that's going to mean that the sine rule is the most appropriate one for us. Okay, so the relationship is going to be XA on sine 60. The relationship is going to be XA over sine theta is equal to L on sine 60. Alright, remembering that you need to use the opposite angle and side. So I can multiply some of this stuff up to make it look a little bit nicer when we take the derivative. So it's going to become XA sine 60 is equal to L sine theta. So now it just becomes a case of needing to take the derivative with respect to time, such that we end up with theta dot in the equation. So remember that when we take the derivative with respect to time, we need to think about which variables are changing with respect to time and which ones are constant. So let's just make a note of that. So L and obviously the sine 60 are going to be constant. L is constant because it's just the length of this rod, which is not able to extend or retract. And we know that XA and theta are going to change with time. Okay, and that's because this block is able to move within the slot, which is going to change the length on the triangle here, and that's also going to be able to change the angle that sits in there as well. Alright, so taking the derivative with respect to time, so sine 60 is obviously constant, so I'll chuck that out the front. And the derivative of XA with respect to time is just going to be XA dot. So on the right hand side, L is a constant that's not changing, so we can leave it out the front. The derivative of sine theta is going to be cos theta. Alright, but then we need to multiply this by the derivative of theta with respect to time, so that's the chain rule. So this is just going to be theta dot. Okay, and what we wanted to solve for, remember, was theta dot, because that we can equate with angular velocity. So rearranging this, that becomes our equation. So the only thing that we have left to do is just double check that we're using only the things that are known inside this equation. So just scrolling back up, so the ones that we're allowed to use are XA, V, and L. So at the moment, what I can do is replace a couple of things. So this becomes omega AB, the thing we're looking for. We're not allowed to use x dot A, however, what we know is that XA is changing with respect to time, this length, and we know that this velocity of the block is equal to V. So again, we can make a relationship between them. So XA dot, the rate that this side length on the triangle changes with time, is going to equal the velocity of the block. So that's something else we can replace in the equation. Sine 60 is just a number, so we can use that. L is a constant that we're allowed to use as well. So the only other thing we need to replace is theta. And if we go back up here, we should be able to write something in terms of theta in terms of the other things in this equation. So let's come over here. So sine theta would be equal to XA sine 60 on L. So theta on its own would just be the sine inverse of all that. So this is just using XA and L, which were variables we were allowed to use. So it's just a matter of popping this in here for theta. So it's going to be cos sine inverse Alright, so if you wanted to, you could probably clean this up a bit so you don't have a cos and a sine inverse with each other, but technically this would be a correct answer since we're only using the knowns, V, L, and XA, and we've solved for the unknown, which was the angular velocity. So that's all there is for that question. See you in the next one.